Okay. So I'd like to welcome you to another edition of Quantum Fluids in Isolation. So this week, I'm very happy to host Dr. Hatem Barghathi from the University of Tennessee. Dr. Barghathi got his master's degree in 2020 from the Missouri University of Science and Technology. And then he got his PhD from Missouri in 2016. And then postdoc from 2016 to 2019 to UVM. And then he postdoc from 2019 to 2020 in the Missouri University of Science and Technology. And then from November 2020 to present, he's been a postdoc with Professor Adrian Del Maestro at the University of Tennessee. And today he's going to be talking about operationally accessible entanglement in fermionic fluids. So please help me in welcoming, either by unmuting yourselves or by clapping virtually, Dr. Hatem Barghathi.
Thank you. Thank you very much. Thank you for the introduction. The topic I will talk about is about entanglement in fermionic systems. In general, it's an inerrant particle system, but the focus will be on fermions. And the idea is to measure the amount of accessible entanglement, meaning that the entanglement that can be used as a resource for quantum information. So to start, for example, we can think of a system of a lattice where we have fermions or hopping around. So they exist in a state that's a superposition of possible occupation of these lattice. And from the, if we want to know the amount of information that's shared between two parts of the system, if we look and consider the spatial modes, so we divide the system to two regions, A and B, or as usually known as Alice side and Bob's side, then we can understand how much there is information or shared information between the two partition A and B by tracing out the degrees of freedom of one of these partitions. So rho A, the reduced density matrix of partition A, we obtain it by tracing out degrees of freedom of partition B from the full density matrix. So this object, the rho A, should contain the information about the entanglement of the system. So for example, now this state of the system, we could measure the amount of information by calculating the von Neumann entanglement entropy given by this formula here, which contains a trace of rho A log rho A, or also we can use the Rényi entropies. That's a more of a generalization of the von Neumann entanglement entropy. We're going to talk in details about that generalization, as it turns out to be important for us. And of course, in the limit when alpha goes to one recovers the von Neumann entanglement entropy. So this is a measure of information, but it has a lot of interesting properties. I'm not going to go through those, but why we want to do the Rényi entropy. What is the benefit of introducing this different generalization? The benefit actually that the Rényi for alpha index that is an integer, let's say 2, can be measured in experiment and also in a quantum Monte Carlo simulation for a bosonic system, for example. So this is easy to calculate, while the von Neumann requires a full state tomography and it's expensive up to being impossible. Right, so that's kind of the general idea about measuring the amount of information. However, in identical particles or systems of identical particles, there is a idea introduced by Wiseman and Vicaro, and that restrict the amount of information that can be shared between these two partitions for a quantum information processing. And the idea here is that having a fixed total number of particles in the system will impose a restriction on the state. and that if you know how many particles on Alice side or the A side, then you know what is the number of particles represented by the state on the other partition or both sides, which was just the complement of that total number of particles. And for this, it means that at any point that you project or you do any operation on partition A, you already know the number of particles here, and that fixes the number of particles on the other partition. So in order to calculate the amount of information that can be accessed for quantum information purposes, then one needs to consider projecting the state for that fixed number of particles in A, and of course, a fixed number of particles in the partition B, and then measure the entanglement or the reduced density matrix after projection, which is the row AN here for that fixed number of particle. And after obtaining the calculated entropy from all of those, one will average all of these entanglement entropy or the von Neumann entanglement entropy using the particle number distribution, which of course simply just the trace of the projected density matrix. So their definition of accessible entanglement, it's a von Neumann measure as it averages out the von Neumann entanglement entropy in these partitions. And thus the existence of conservation of number of particles eventually reduces the amount of entanglement that can be shared between the two partitions. So let's kind of think about this also in a different way. One can show that the accessible entanglement could be written as the total von Neumann entanglement of the system, subtracting the Rényi or the Shannon entropy of the particle number distribution, just the classical information in the particle number distribution. So that tells us that the accessible entanglement is simply the total entanglement, and we get rid of the amount of information that is due to particle number fluctuation, and this is cannot be accessed to for quantum information purposes. To look at this in more details, let's consider a very simple example. Let's consider that we have a system of four sides, we have two fermions, and we look at a very simple state. It's a flat state where we kind of have all possible configurations of the two fermions with equal weights. They're all positive equal coefficients. Now, we can now calculate the reduced density matrix by tracing out the B degrees of freedom, and we get row A as it's represented here. Now, we see that before moving on with the calculation of the von Neumann entanglement entropy, it's important to recognize something here, that it's always the case that you get the reduced density matrix in a block diagonal structure. And this is actually due to the conserved number of particles. So you see that this first kit here, partition A has only zero particles, sorry, and partition B 2 particles, and this is not connected to any other elements in the system, and that you cannot have more than 2 particles in the total system. So this is a property of the reduced density matrix that's always a block diagonal, and the elements of those blocks, of the partial traces, the trace that you can calculate from any of these blocks will give you the particle number distribution. So just an idea of how this structure will become useful later when we want to calculate accessible entanglement. Now, if we simply just take this matrix and diagonalize it, and of course we are just diagonalizing the inner part here, the 2 by 2 matrix, which with the 45 degrees rotation, we get a diagonal matrix, and we have the eigenvalues of this density matrix from lambda 1 to lambda 4. And of course, calculating the von Neumann entanglement entropy, applying this formula, which was the trace of row A log row A, we just plug in the eigenvalues of the density matrix, and we get some entanglement, total entanglement in that system. Of course, we can do the same for the Rényi entropy, where we use the eigenvalues that give us a simpler picture that will be useful also later in deriving some of the important results. So this is the total entanglement. But now, for the same state, we can also think of calculating the accessible entanglement, which means that each time we're going to project this state on a fixed number of particles in partition A and B. For example, if we consider only 0 particles in partition A, so we only get the first kit. That's the same if we consider 2 particles, then we get the last kit. 1 particle, we have these 4 kits are contributing to this, having 1 particle in partition A. So this means that each time we're going to project the density matrix and then diagonalize it. And what we get in that case, that the density matrix for 0 particles has only 1 non-zero entry, it's equal 1, similar for 2. And in the case of 1 particle, again, diagonalizing this after renormalization that we did here, that we have a trace of 1 always, we get also a matrix with 1 non-zero entry that's equal 1. In this case, all of these matrices contribute 0 entanglement, and then of course the overall average is 0. So we see in that state there is total entanglement, but there's 0 accessible entanglement based on that definition. Right. So now that, okay, we go back to that that idea that we can calculate the von Neumann entanglement and the accessible entanglement entropy for that simple system. But if we want a measure that is accessible or can be measured in experimental and quantum Monte Carlo simulation, we want a Rényi generalization of the accessible entanglement. So for example, for alpha 2, we know that we can calculate or measure the experimentally S2, but we want to have S2 accessible. So what is the S alpha accessible form and how it looks like? So one might expect that it's simply one can just plug in S alpha here and do the average. It turns out that's not the case, as we're going to see. It will violate some restriction. Doing this will violate some restriction on the accessible entanglement. So how to get to a generalized accessible entanglement? We'll think about first two things. The first is to find a Rényi generalization of accessible entanglement. First, we need to understand how the von Neumann entanglement entropy is related to its Rényi generalization. So what kind of generalization is happening, in what terms? So we know that alpha 1 give us back the von Neumann, but how we understand going from alpha 1 to general alpha in that case. The other thing is how we can restrict this measure of S alpha accessible, meaning that what we know is that the difference between the total entanglement and the accessible entanglement, what we call delta S alpha here, must satisfy this inequality here, which simply saying that the difference must be positive. So we cannot gain more information by due to conservation loss. And also in the same time, the total loss of information cannot exceed log of d, where d is the support of the particle number distribution. So saying that if we have a flat probability distribution for the particle number, that's the maximum possible amount of information that we can lose. And thus the delta S alpha must be must satisfy this inequality here, positive and less than log of the support. So let's now kind of visit the first part, which is the generalizing the von Neumann entropy in terms of a Rényi entropy. In order to understand this, well, that's kind of how to write the von Neumann and the entanglement entropy in terms of the density matrix. But if we know the spectrum of the density matrix rho A, we can write this in terms of the spectra, which give us a simple form of a summation instead of trace, a product instead of determinant. So it's just a more explicit form that we can help us compare the two measures. So the von Neumann entanglement entropy simply now is just negative the sum of lambda I log lambda I instead of minus trace rho A log rho A. But if we try to pull this log outside, so it means that it's a log of lambda to the lambda, or effectively it's minus the log of the product of lambda I to the lambda I. So that's the von Neumann entanglement entropy. negative log of a product of lambda I to the lambda I. We can do something similar to the Rényi entropy. We already have the log here, but just we insert this coefficient as an exponent, keeping the negative side sign out. And what we get that structure. So what I did here, I just pulled one of the lambdas up front. So I have lambda I to the alpha minus 1 instead of the total lambda I to the alpha. So I did nothing with the measure. But looking at that structure, one sees that what's inside here looks like a geometric mean. If we think of the exponent lambda I as a probability distribution of some positive entries, then this takes a structure of a geometric mean. While the Rényi entropy, what's inside the negative log, takes a structure of power mean. So this suggests that the von Neumann, generalizing the von Neumann to a Rényi entropy, is basically by turning a geometric mean to a power mean. And of course, when the power, the alpha minus 1 goes to 0, the power mean becomes a geometric mean. Right. So with this idea, let's kind of try to apply the same thing to the accessible entanglement. We have a von Neumann definition of it, and let's try to write this in terms of the spectra, not of the total density matrix, but the combined spectra of all the projected density matrix. So the spectrum of rho AN is given by lambda n, and the I just an index that runs over the entries of the eigenvalues of rho AN, the non-zero eigenvalues more appropriately. So if we have this, and then we just kind of plug that definition as we did before for the von Neumann entanglement entropy, we get the negative sign out. But just rearranging, what we get is that the accessible entanglement is a negative log of a geometric mean using the probability distribution of particle number as the probability of it. And the entries are a geometric mean that's done locally in the projected density matrix rho AN. So this suggests that if we want to do a Rényi generalization, then the most general thing to do is to turn both geometric means to power means. The inner power mean, that is a generalization of this, it's obvious that it must have an exponent of alpha, or the effective power of alpha minus 1 for the generalization, that there's an alpha into or lambda to the alpha multiplied by lambda to the alpha minus 1 inside here. But the other exponent is not determinate yet. Turning this outer geometric mean to a power mean with some power, it's not determined, but this gives us the overall or the general structure of how the accessible entanglement entropy or the Rényi generalization of it, how would it look like? So it's a power mean of a power mean. We know one of these powers, it's the alpha minus 1. The other power we call gamma. Possibly it's a function of the parameter alpha. So the next thing is to try to see if we can determine what this exponent is. So in order to do this, we go back and consult the inequality that we already have on the delta S alpha, the difference between the two. And when we look at this, we find that actually there is only one possible value of gamma, or of a gamma dependent on alpha, that the gamma must be alpha minus 1 over alpha. Otherwise, you cannot guarantee this inequality to be satisfied in general. While for this value of gamma, it is guaranteed that this will be satisfied in a general sense. So how we achieve this is by considering a simple example, but in a sense it's special, that help us get to the dependence of gamma on alpha, the two exponents. So in this example, what we are considering that each of the rho AN has equal eigenvalues, but the number of eigenvalues is given as L to the n, where L simply just an integer that is greater than 1. It could be the partition size, or it doesn't really matter because we are just looking at the spectra, not at the state itself. And this means that if those eigenvalues, the L to the n eigenvalues, are equal, and from the normalization they have to add up to unity, it means that each of them should be L to the minus n. So now we know the eigenvalues for a block of n particles. Also, the particle number distribution, that's another freedom that we have to kind of choose. We have the freedom to choose the particle number distribution for that overall spectrum. We choose it such that it's exponential, it has this exponential form. So with this particle number distribution and these eigenvalues, now we can calculate both the Rényi entanglement entropy as well as the accessible entanglement entropy. So now here we focus on the case of alpha greater than 1, because we are mainly interested in integer values of alpha 2 and above. But we're going to see that this results actually comes to be quite general. So the Rényi entanglement entropy for alpha greater than 1 of that obtained from the spectra has that form. We see there's a leading term that goes as square root of n. While the accessible entanglement in general, we can consider different cases where the gamma is positive or negative or equal to 0, and we have these different scaling. And we see that the accessible entanglement has a scaling with n, and the corresponding Rényi scales with square root of n. So there's obviously, this eventually will be larger than S alpha. So let's focus on the difference between the two that simplify how this looks like. So the delta S alpha then for gamma less or equal 0 is negative, which means that gamma cannot be less or equal 0. For gamma greater than 0, it gives us that formula here. But of course, we can see that if 1 over gamma is less than alpha over alpha minus 1, we end up with a negative difference. That's, of course, we want to avoid. However, if it's the other way around, if 1 over gamma is less than alpha minus 1, of course, that's positive. But asymptotically, the difference goes with the square root of n. But we want it to be less than log of the support, and the support should be eventually proportional to n. So it should be less than log m plus 1 or equal to that. So it means that we have a violation of one side or the other as we choose any value of gamma, except if it's alpha minus 1 over alpha, where this leading term vanishes. So this inequality is violated for any value of gamma except gamma equal alpha minus 1 over alpha. So this is, of course, for alpha greater than 1. The same conclusion could be obtained for alpha less than 1 if one simply just flip around the probability distribution, meaning that effectively we replace a little n by n minus n in all of in that term. So just flipping around the probability distribution will lead us to exactly the same conclusion for alpha less than 1. So in all scenarios, alpha greater or less than 1, the gamma cannot be any value except alpha minus 1 over alpha. Now the question is the inequality satisfied for that special value of the exponent. And if we look at now this measure, if we now write it in terms of the density of projected reduced density matrices and the corresponding alpha measure or S alpha of these matrices, it takes that that form. If we define now an auxiliary probability distribution, we call P and alpha, simply just by raising the density matrix to the power alpha. And remember, rho A is a block diagonal, which means that effectively we are raising each of these blocks to the power of alpha. So there's no mix when we, these blocks, they don't mix as we raise alpha rho to any power of alpha. Let's think of integer at that point to make it even much clearer, which is of course true also for non-integer values. And then we project on a fixed number of particles, we take the trace, and then we normalize with the trace of rho a to the alpha. This probability distribution is not the particle number distribution, but of course it's just an auxiliary particle or probability distribution that takes the same index as the particle number distribution. So there is a probability for each n value. With this definition, we can write that difference, the delta S alpha, as the Rényi, classical Rényi entropy with index 1 over alpha. See, there's a flip in the index of Pn alpha. And of course, that is because it's the classical Rényi entropy with some probability distribution of some index. This is definitely positive. So this satisfies, we guarantee that the left side of the inequality is satisfied. Also, the number of entries of that probability distribution is the same as Pn, which means, of course, that also will satisfy that the result of this will be less than log of the support. So that definition satisfies the conditions of delta S alpha satisfying the inequality, as well as it's a proper Rényi generalization of the accessible entanglement. One more thing about this is to ask about what is the difference between the accessible entanglement and the total entanglement, and this is the von Neumann, where alpha is equal to 1. And the difference between the two is actually always equal to the Shannon entropy of the particle number distribution. So that means that what we are subtracting as we calculate the accessible entanglement is the classical information that is stored in the particle number distribution. However, for the generalized measure, the delta S alpha is not equal to H alpha of Pn as one will expect. It's equal to H of 1 over alpha of Pn alpha. And that will take that form. So it's not exactly, the difference is not exactly the classical Rényi entropy of the particle number distribution. However, it could be equal to the Rényi of the particle number distribution if the particle or the auxiliary distribution Pn alpha is proportional to Pn to the power of alpha. And of course, the proportionality could be fixed by the normalization of Pn alpha. So in this case, we recover this results. And in fact, this is the case for the example we considered earlier, where each of these blocks have a single eigenvalue, so that is satisfied, and it means that the total entanglement, that example, was simply just the Rényi, or the classical Rényi of the particle number distribution, or effectively the von Neumann. Right. So that's kind of the idea of this generalized measure, that we have now a Rényi generalization of the accessible entanglement entropy that we can measure in experiment and in quantum Monte Carlo simulation as well. Now, the next part I would like to talk about, looking at this measure, the accessible entanglement entropy, the von Neumann version, and also the one we just introduced as the Rényi generalization of the von Neumann entanglement entropy. So this accessible entanglement we want to consider in a system of interacting particles. And we want to consider very simple particles, or specifically fermions. So we're going to look at the fermionic Hubbard model, or what's known as the TV model, related to the parameters, where we have a hopping parameter T and interaction strength V. We allow here only hopping to next neighboring sites, and also interaction between nearest neighbors in the system. And that model can be mapped onto the XXZ model, where with one extra condition, that one need to fix the magnetization, but the total magnetization is fixed because of the fixed number of particles that we are considering in that case. So that's conservation of number of particles is applied as well here. What's interesting about that model, it's a very simple, and of course it's an integrable model, but it has, compared to its simplicity, it has a rich phase diagram that starting from a very negative interaction, very strong negative interaction, we can see that we are in the cluster solid where the fermions cluster together, and they could be in any position just from the translational symmetry of the system. So that's the exact state at infinite negative interaction. And as we move to the right by reducing this negative interaction, when the ratio between the interaction strength and the hopping parameters is at -2, there is a first order transition that happens at that point. And the state in this case is exactly the state that we looked at earlier. It's a flat state with all positive coefficients. And if we continue across that transition, we enter the Tomonaga-Luttinger liquid phase of this fermionic system. And this is just the free fermionic state. And from that, there's another continuous transition at ratio of V over T equal to 2 to a charge density wave, where the fermions at half filling try to avoid each other by cubing every other site in the system. And always there's two possible configurations, again, due to this translational symmetry. So this is just an overview of the model. Now, what we want to look at, the accessible entanglement and the total entanglement in the system as we move from the negative infinite interaction to a positive infinite interaction, and what happened across the two first order phase transition and the continuous transition in the middle. So a general result that we obtained through exact diagonalization of the model, and this is at half filling with half partition, we calculate the total von Neumann entanglement entropy, the S1, and also the accessible entanglement. That's an old figure, so the name used to be operational entanglement, but now it's accessible or operationally accessible entanglement entropy, meaning that this is exactly what we just discussed earlier. That's the von Neumann accessible entanglement entropy, and that's the Rényi, second Rényi accessible entanglement entropy. So if we look at the overall entropy at a very negative interaction on that side, we see that there is some large amount of entanglement, and then there's a drop near the first order phase transition that's almost saturate in the Tomonaga-Luttinger liquid. And this could be understood as the leading term could be calculated here and has no dependent on the interaction or, of course, the corresponding Luttinger parameter. And then across the transition or the continuous transition, that there's the total von Neumann entanglement start dropping and reaches the final saturation value around log 2 this point. But if we look at the accessible entanglement, let me ignore the von Neumann for that, just to zoom in and look at even larger system sizes. We see that the accessible entanglement starts from a value that is asymptotically will saturate at a constant, which is around log 2. This is in the cluster phase. And actually at the first order transition, the accessible entanglement is exactly 0. And in this case, the total entanglement is nothing more than the Rényi of the classical Rényi of the entropy of the particle number distribution. So there is no entanglement, just vanishes at the first order transition. And then we see that in the Tomonaga-Luttinger liquid, there's a dependent on the interaction strength, or effectively the Luttinger parameter, in opposed to the total von Neumann entanglement entropy. And we look at both the blue here is the von Neumann entanglement entropy for different system sizes, as well as the second Rényi entropy. And we see that the measure that we generalized looks compatible with the total or the von Neumann version of the accessible entanglement. And there's also, we see a peak that start to appear as we increase the system size, as the peak increases in height near the continuous phase transition. And then eventually for odd number of particles, there is 0, or it's saturate at log 2 for even number of particles. And that is simply just because when you have an even number of particles in the density wave phase, then the two possible kits that you can look at here will have exactly the same number. So that's an example. We have 2 particles over 4 sides, so even number of particles. For both of those, there is 1 particle on each side. However, if you have an odd number, then always the 2 partitions never have the same number of particles, and that kind of give us the difference of a log 2 at this point that goes to 0 for odd, and it's log 2 for even number of particles. So this is the results for this flat state, where one can show exactly and prove that it's always a flat state at this point for any filling fraction, or for also the result is the same for any partition size. Now, if we look at the Tomonaga-Luttinger liquid phase, we see there's a dependent here, but also there's something interesting about the particle number distribution and the auxiliary particle number distribution, P and alpha. So both of them are Gaussian with the same mean. And also the variance of P and alpha is equal to the variance, asymptotically equal to the variance of Pn divided by alpha, which of course for a Gaussian distribution means that P and alpha is asymptotically proportional to P and alpha, which again, we recover that relation, that the difference between the total entanglement entropy and the accessible entanglement entropy in this phase is approximately equal to the classical Rényi entropy of the particle number distribution. So in this case, we see that if we test this dependence on in the for the particle number distribution by simply just rescaling the P and alpha to the power of 1 over alpha, we see that all the data collapses on the same results for P and alpha, and that's true for the system of either odd number of particle or even number of particle, and that's calculated inside this Luttinger phase at interaction minus 1.5, where the phase exists between -2 and 2. However, if we go out of that phase, if we look, for example, in another extreme where we have the cluster phase at a very negative value of the interaction, we see that this collapse breaks down, that the distribution is almost flat, but it's not quite there. And we see that there's a difference even after rescaling the P and alpha with this measure, which of course suggests that the difference here is not equal to H alpha of Pn in this case. In the positive interaction, also we see this behavior here. It appears to be there's some collapse here, but this is not really a true collapse over all the entire distribution. This is simply just due to the separation of scale on that logarithmic scale here, and the fact there's 2 entries for each of these values, and that's kind of breaks down after a few points, and we see that the collapse is not happening. In addition, that this distribution is very narrow distribution if we compare it in these 2 cases. So that's the behavior of accessible entanglement, or at least the different reduction that's happening in the Tomonaga-Luttinger liquid. compared to the other two phases that we just looked at. But also, there is another interesting feature that we have seen here, which is the peak near the transition. And we want to look at this in more details and to see if this peak or the position of the peak could scale by how far we are from the critical value of 2, where the infinite system transition happens at, and if there is a finite size scaling. However, with the exact diagonalization, there is no much room to do such calculation. We're limited up to 16, at best 17 particles if we want to do that. So to investigate more, because it's interesting to see that this measure of entanglement or accessible entanglement that's going to be more quantum, where we're getting rid of some of the classical information in that measure, is trying to tell us something about the transitional scales of the transition and provide a very obvious signature if we compare this with the total von Neumann entanglement entropy. And in order to do this, we needed to go to larger system sizes. So we perform a density matrix normalization calculation using the iTensor library, which is a very interesting and very powerful tool that allow us to go up to 49 particles in this system. And we kind of combine the DMRG calculation and the exact diagonalization. And we can, by just assuming that the value of the interaction at which the peak appears and the distance from the asymptotic large system transition or critical point at 2, that the difference have a power law scaling of that form, where n is the number of particles, and of course n is proportional to L, or effectively it's just the system size divided by 2, as we always consider half filling in these calculations. And from this we can see, and obviously there is a scaling that suggests that the value of the exponent 1 over mu is around 0.3, and this suggests some correlation, maybe length exponent accompanying this transition that asymptotically happens at 2. So that's just we're just looking at this transition and trying to investigate further what could we learn about the transition and the relation between this scaling and the actual transition that goes in that point. So right, so I think with this came to the end of the talk, and thank you very much.
Okay, so I actually have 1 or 2 questions, but first, maybe if anyone else has a question, please feel free to unmute yourself.
Let me ask. Can you hear me?
Yes,
Sorry.
we can.
Yeah.
So is there any dependence on boundary conditions? Like, you didn't mention anything about the open boundary condition or periodic one.
All right, I think it was in the system is all periodic boundary condition. I thought I mentioned that in the beginning in describing the system. Sorry if I missed that. Yeah, it's periodic boundary condition that makes most of the calculation easy with exact, especially with exact diagonalization in that case. But
so there is no any boundary condition dependence, right? As far as I understand.
Yeah, the boundary condition could affect these results, but in terms of just a subleading corrections, but not in one way of looking at this. Even if you consider like the asymptotic scaling of the Rényi entanglement entropy, there is a prefactor of 1/2 that you have to introduce if you consider fixed boundary condition in a positive periodic boundary condition. So that's there is that kind of dependent there. But most of the definition of the measure and its generalization should work with both, of course, periodic and fixed boundary conditions.
Okay, thank you.
Okay, any other questions? Okay, maybe, so I have sort of a two-part question. So the first part is, how could we extend this to higher dimensional systems? And then the second part of the question is, if we can extend it to higher dimensional systems, do you foresee a way of trying to understand accessible entanglement, connecting that to, say, like the Landau parameter of a Fermi liquid?
Right. So for the first part, if we look at higher dimensions for in general, the measure could be also applied for higher dimensions as the structure of density matrix just get more complicated. We actually, I just didn't thought I will have the time to go through details about higher dimensions, because we looked at, for example, at free fermions in any dimensions, and one can see that indeed the accessible entanglement is less than the total entanglement of the system, and when we derived, in fact, the full scaling of that. And the interesting thing about it is that in fermionic system, the loss of the entanglement due to particle number conservation scales as the log of the total entanglement, which means that you don't lose much. And that's true in any dimensions for free fermions. And but for the for higher dimensions with the interaction parameters, numerically it can be accessed, especially for some of the simple cases. But we didn't look at this in details. We just looked at non-interacting, maybe fermions in general, but not with interactions. Of course, you can also ask the question about the spin. If you have a spin in the system, what role that does include if there's a spin interaction as well.
Mm-hmm. Okay. Any other questions?
So as far as I understand, usual entanglement entropy with von Neumann, it behaves differently on these quantum phase transitions, right? Whether it's topological or it actually doesn't matter. So which kind of new peculiarities this accessible entanglement can give? So
you mean the difference between the von Neumann entanglement entropy and the von Neumann accessible entanglement entropies? That's
yeah. So so the idea is to capture these phase transitions, right? To show
right. Right. So I don't know if I'm still sharing the slides.
No, you are not.
Oh, okay. I just am I now?
Yes.
Okay, cool. It's an interesting question, actually, because if we go back to this picture here, right? This is the red curve is the total von Neumann entanglement entropy, and we see there's a kind of a peak that start showing it tell us that the accessible entanglement could be more sensitive to phase transition than looking at the total entanglement. If we look at the peak that's developing here, so in one way, one can think of this like if for example, if we can come up with the order parameter for the transition here from the total von Neumann entanglement entropy, we see that the accessible entanglement is effectively behaving as a derivative of that measure. You can think about it as like magnetization and susceptibility, for example. So it's more pronounced and can be found easily, then looking at the total entanglement entropy. And simply we just got rid of the particle number distribution contribution to that. Does it answer the question?
Yes, sure. So for me, it's interesting how this accessible entanglement entropy like behaves in the other type of quantum phase transitions, like
Oh, I see.
phases or many body localization ones. So it's very interesting actually.
Right. Actually, that was the first study of this accessible entanglement in interacting systems. So, of course, yes, there's a lot of questions about like what happens in other systems. And also, this first order phase transition, the vanishing of this accessible entanglement, is it a feature of the first order phase transition, or just by coincidence because this is an integrable model with infinite symmetries in it? Or could we look at non-integrable system and see something similar? Right.
Yes, so if it behaves like this in integrable, it means a lot. I think it should show up similarly in this many body localization phase transition, I believe. Because there you have also this local integrals of motions which emerge, and you can catch this phase transition by this zero accessible entanglement entropy. So
right. I think so. Yes, for localization, because effectively then you're fixing somehow the mode. I mean, in an infinite interaction strength or infinite disorder, right? And that's effectively what you expect accessible entanglement in a localized phase to be much less than in a non-localized phase, if we compare this with the picture we see right now. Between the density wave and the Luttinger liquid phase.
Okay, any more questions? So if not, let's thank Dr. Barghathi again.
Thank you very much. Thank you.
I would like to thank you especially because it was very nice and technical presentation.
Well, thank you. I was thinking about it in preparing this. Should I give more details, or just some of these measures and these details are not known for the people, so I thought maybe going in detail will be more useful. So thank you for telling me that. Thanks.